All right, thank you all for coming. It's a great pleasure to introduce Ken Shen, who I have known longer than any other astronomer, because we went to high school together.
That's true.
But Ken did his PhD at UC Santa Barbara, and then moved to Berkeley, and has been unable to tear himself away from there ever since then. Except today. I've seen him in Tucson.
This is how important you people are to me.
That's right. That's right. So Ken has done some really pioneering work on supernova, 0.1A supernova, and had, I think, one of the fastest Gaia results of anybody else.
There were a couple before.
He was very, very quick. Told me that he was up at like 3 in the morning trying to get the paper written, which seemed kind of painful, but very
For theorists,
impressive.
that's rough, yeah.
Yes. It seems like something only observers do. But anyways, I'll let him tell you about all of his exciting discoveries.
Thank you. Thanks for having me. It is true, we did go to high school, and I will be selling yearbooks with Kaitlin's name in the lobby afterwards, so just come find me. Right, so what I want to talk about today is work that I and others have been doing. There's some good stuff in that yearbook. She was very active in the drama scene. Anyway, so oh yeah, is that true? Right, back to science. I want to talk about what I believe has been a revolution in how we understand how type 1A supernovae happen, and a revolution that's been happening very recently. So just in the past, I'd say 5 to 10 years, what we think is the main progenitor of type 1A supernovae. A lot of people were focused on one scenario, and now the field has kind of exploded into a different, people exploring different alternative scenarios, and I'll be talking mostly about what I believe is the main scenario for type 1A supernovae. Okay, first a tiny bit of motivation, although I probably don't need to motivate much for this crowd. Hopefully we all know, we've heard about type 1A supernovae and their use in cosmology. It was really realized in the late 80s and early 90s that while type 1A supernovae are not exactly standard candles, they're standardizable. Okay, and so their peak luminosities can be related to how fast their light curves evolve. The more rapidly evolving ones are dimmer. And as a result, you can normalize them, you can standardize them, make them into standard candles, use them as distance indicators. And it was the first major piece of evidence that the universe's expansion was indeed accelerating. They're also important for cosmic nucleosynthesis, not as important as some other things are in filling out the periodic table, but fairly important for some things. So type 1A supernovae are in the light blue. They're important for intermediate mass elements, things like silicon and sulfur and calcium, as well as the primary source at redshift 0 of iron group elements, things like iron and cobalt and manganese and nickel. Okay. But this is not why I study type 1A supernovae. I think they're just pretty good and fun to study. And very interestingly, despite however long we've observed them and however long we've been studying them, and despite the recent claims, we still do not definitively know what leads to a type 1A supernova. So some of these papers, you may see their splashy titles are associated with the journals that they are coming in. Some of these papers, the putative systems that the 1A was supposed to have come from, those identifications were later rescinded or found to not be true. For these more recent ones, the evidence is decent, but these are not regular type 1A supernovae. These are peculiar supernovae. And so what I've been working on for the past 5 or 10 years has been what gives birth to regular type 1A supernovae, the bulk of 1As that we see. So let me first start with what we as a community mostly agree on, what basic properties of type 1A supernovae that we agree on. So I showed a light curve before. Here it is in bolometric luminosity. Roughly, they rise to peak and fall from their peak in something like a few weeks. And equating the time of an expanding ball, the time it takes photons to get out of that, to the explosion time immediately gives you some sense of how much mass is involved in explosion. And very roughly, it's something like a solar mass, 1 solar mass of ejected material. So that means they're not coming from very massive stars. These are not 20 solar mass explosions. They're roughly a solar mass. The spectra tell us basically what has been produced inside the explosion. The hallmarks of a type 1A are no signatures of hydrogen or helium, and strong signatures of intermediate mass elements and iron group elements. In particular, these very strong silicon feature here, as well as calcium features, iron group features as well. Okay, so whatever's exploding had better produce silicon and sulfur, as well as iron group material, and it has to probably come from an evolved star because there's no hydrogen or helium. Oh, and I should also say that the light curve is very well matched by the roughly 1 solar mass of material, roughly half of it or something like that, being produced as a form of nickel-56. It's radioactive. Its decay through cobalt to iron matches this light curve very well. The last major piece of evidence is that they're seen in both young and old galaxies, both late type and early type. And so whatever is producing them had better be produced at roughly something like 100 megayears, but also has to last for a very long time, out to of order 10 gigayears even. Okay, so whatever is being produced had better be something that is produced early, but also sticks around. And finally, they're fairly common. There's something like 1 type 1a for every 1,000 solar masses that's produced. Okay? And so the model that almost everyone in the 1A community believes, or basically everyone believes, is that it's some sort of thermonuclear explosion of a carbon-oxygen white dwarf. And that carbon-oxygen white dwarf burns through fusion up into intermediate mass elements and iron group elements, giving some mix that's seen in type 1A supernovae. Confining ourselves to white dwarfs, something like 1% of all white dwarfs that are produced in a Hubble time have to explode as a type 1A. Okay, so it's not every white dwarf, that's good, but it's some fair fraction of them. And of course, stop me at any time if you have questions. Okay, so this is something that most people agree on. As we all know, though, white dwarfs on their own are very stable, need some way to set it off. And so the name of the game has been, for the 1A progenitor question, what is the progenitor? What causes that white dwarf to explode? Not everyone in the 1A community believes this, but almost everyone believes that there's some binary companion. So there's another star in a binary system that somehow triggers the 1A to go off. Classically, at least since the 80s or so, people have discussed 3 historical progenitor scenarios. Okay? The first one, which I'm sure you've all heard about, is the single-degenerate scenario, so named because the companion star is a non-degenerate star. So there's one degenerate star in the system, the white dwarf. It accretes material from a non-degenerate star. That white dwarf grows up to the Chandrasekhar mass of 1.4 or so solar masses, at which point the density inside the white dwarf starts to get very high enough that carbon can start to fuse. And finally, after some core convection, that eventually leads to the birth of a flame. Deflagration that transitions into a detonation. I'll define these terms in a few slides. The second classical scenario is what's termed the double degenerate scenario. As its name implies, there are 2 white dwarfs. Okay? They merge together, form something that's larger than the Chandrasekhar mass, and then the explosion mechanism is exactly the same as the single degenerate scenario. There's carbon fusion in the center because the density got very high, core convection, and then the birth of a flame. The final scenario that people hadn't discussed as much in the 90s and 2000s, but we have started discussing more, is called the double detonation scenario. And in its historical incarnation, it was actually a single degenerate scenario. The companion was a helium-rich, non-degenerate star. Okay, so it's already kind of confusing because when most people think of single degenerate, it's accretion from a hydrogen-rich star, grows up to the Chandrasekhar mass, and you get an explosion. For the classical double detonation scenario, it's a helium-rich star, it's non-degenerate, okay, so it's a single degenerate scenario, but the explosion mechanism is quite different. So in this scenario, helium is piled up on the surface of a sub-Chandrasekhar mass white dwarf, something like 1 solar mass or so. That helium then detonates, and that triggers another detonation in the core. So it's a double detonation scenario. So historically, people discuss these 3 scenarios. However, even after having explained that to you, I want to try to go away from using those names because, as I alluded to, the naming is kind of confusing. In particular, it's convolving the difference. It's convolving what the progenitor star is, what the binary companion is, with what the explosion mechanism is, and mixing those 2 can be confusing if you don't know exactly what you're talking about with the person that you're talking about it with. So in this table, it's showing what the companion is, a hydrogen-rich star down to another white dwarf, and how matter is being accreted from that companion, whether it's stably through an accretion disk or unstably in some sort of merger. And on the x-axis, it's showing how the explosion happens, okay, whether or not it's a Chandrasekhar mass scenario, core convection, and then the birth of a flame, or a double detonation scenario in which there's a helium detonation and then a carbon detonation. There's also a class of models, which I won't discuss, in which the carbon can be detonated immediately during the merger, where there's no need for a helium detonation. But I'm not actually going to talk about those. The ones I'll focus on in this talk are these squares, or rectangles. This is where the classical single-degenerate scenario lives. So hydrogen-rich, stable accretion up to the Chandrasekhar mass. This is the classical double-degenerate scenario. Two white dwarfs merge, and the merger remnant is larger than the Chandrasekhar mass. But again, it's the same explosion mechanism. And then double detonation scenarios involving two white dwarfs. So again, confusingly, these are double degenerate scenarios, right? They involve another white dwarf, but the explosion mechanism is a double detonation. Okay, so these are double degenerate double detonations. Right, so these are the ones I'll be focusing on here. Okay, any questions? Moving on.
Can you tell us what is the direct seed definition?
Yeah, so that's a model where two white dwarfs merge. Instead of igniting helium, so it's a double detonation, these papers just kind of, they didn't have the resolution to have the helium. If you ignore the helium, you might get to the point where you just directly ignite the carbon. So I don't know, it got this name, and people often say violent merger, but we had to differentiate violent mergers from merging white dwarfs that had double detonations. Yeah, so the nomenclature is indeed confusing, and in the model that I favor, we tried to be very specific about what was exploding and how. All right, so I'm going to start by, I guess, sort of picking apart the scenarios I don't agree with, explaining why not just me, but many others in the field have moved away from these historical scenarios and potentially towards these boxes here. And again, these were the classic scenarios. These were the ones that the majority of the people in the 1A community were working on up until the 2000s, or even the late 2000s. And since then, people have started switching. All right, so this is the classical single-degenerate scenario. Okay, so the idea is there's some non-degenerate star, material is being pulled through an accretion disk onto the surface of a white dwarf. It piles up onto the surface of the white dwarf, growing it up towards the Chandrasekhar mass, at which point the idea is the density at the center of the star is very high. You get density-driven fusion, something that is often referred to as picnonuclear ignition. That fusion leads to a big convective core, something like 1,000 years it's simmering like this, and finally it leads to an explosion. There's a cartoon of how you might expect to get one of these systems. So you start with two main sequence stars. One of them evolves up the giant branch, and then there is this common envelope event. As you all probably know, we don't fully understand common envelope events, but something like that must happen because we observe close-in systems where a white dwarf is with a main sequence star closer than it could have been as a giant. So something like a common envelope must happen to get these very close binaries. For some of those systems, then they come into contact and hydrogen is being pulled off the non-degenerate star. Now I've mentioned the words deflagration and detonation. I just wanted to spend a slide defining those in case you are not familiar with flame physics. So the very basic definition has to do with whether or not they're faster than the speed of sound. Okay, so deflagrations are flames that are subsonic, detonations are supersonic, and so they're propagated by a shock. There's a shock wave associated with them. And this movie I'm going to show is not actually a 1A simulation, it's terrestrial combustion, but I like it because A, it looks very nice, and B, it shows both a deflagration and a detonation. Okay, so this is methane burning in a tube. One property of deflagrations, they're subsonic, and so there's time for the fuel to communicate with the material upstream, right? There's time for sound waves to move around. And so the flame fronts can be very wrinkled because of the interaction between the fluid velocities and the flame. And you'll see that this transitions in this particular case into a detonation. It turns from subsonic into supersonic. And very qualitatively, you'll see a very distinct change because the detonation is supersonic, it can't communicate upstream. And so it turns into something very smooth and planar because, again, the fluid velocities upstream can't affect it. Okay? So there's a difference, subsonic deflagration, supersonic detonation. Deflagration allows for communication upstream. The white dwarf can react to the burned material. The detonation, it can't react. This is how this plays out for the single-degenerate scenario. In its modern incarnation, it has both a deflagration and a detonation. So it has to be both. And the reason it has to be both is if you only allow for deflagration in a white dwarf, it doesn't actually burn the whole star. Okay? Okay, so in this simulation, they have a deflagration. It's exploding out of the star. As you can see by this frame, there's all sorts of regions where some of the material is not burned. That's just because the deflagration is very wrinkled. It doesn't immediately just subsume all the fuel into these bubbles of burning ash. Some of the fuel remains unburnt. They then need to put in a detonation by hand. Okay, so the blue contours are showing the surfaces of that detonation. And that detonation then sweeps back through and burns the rest of the material. Okay? So the combination of a deflagration and a detonation with a transition in between allows the Chandrasekhar mass single-degenerate scenarios to look roughly like a 1A supernova. If you only had the deflagration, you wouldn't burn enough material. If you started from time 0 with the detonation, you actually burn too much material. You burn all of the material into ash. And you want a mix of the two. Okay? So you need a deflagration and a detonation for these Chandrasekhar mass scenarios.
So if you're putting in this by hand, what is not happening that needs to happen?
Sorry, if you're putting...
You said you put in the detonation by hand.
That's right.
And so what is not happening in deflagration that causes that? What are the conditions?
Right, so it's put in by hand because, you know, as you probably know, flame physics is very local, and these are global simulations, so there's no hope of resolving the deflagration or the detonation or the transition between the two. All this is subgrid physics. The detonation is put in hand. Well, I think, historically, I think it was put in because it gave the right answer, but it was also motivated. But there is, you know, I don't want to badmouth it too much. It is physically motivated. There are some arguments where, as the deflagration is moving into lower density material, it becomes more and more turbulence, and that turbulence might mix the fuel with the ash in such a way to possibly lead to the initiation of a detonation.
And in the combustion literature, whether a deflagration can proceed to a detonation has only been observed either in the lab or in a calculation in a confined
It's
space
precisely
with
right.
walls. And if you don't have walls, it's an open question whether in fact it could even actually occur at all in an open situation like this.
Yep, that's precisely right. So they do observe these transitions in real life, in say factory explosions sometimes, but it's always at some interface where the flame hits a wall or goes around a corner or something like that. For open simulations where there's no obstacles and no broken symmetries, they don't get that. I think most calculations do not see a transition. Okay, if you do allow for the transition and you also have this detonation, it gives you a mix of nucleosynthesis that looks roughly like a 1A. The explosion, observables, light curves, spectra roughly look like 1As, and so people have been pushing on this for decades. However, even after all that pushing, it wasn't perfect by any stretch of the imagination. So this is what's known as the Phillips relation. It's showing the peak magnitude of the supernova versus some proxy for how rapidly it's evolving. So more rapidly is that way. So brighter things evolve more slowly, dimmer things evolve more rapidly. The green are the observations, and the gray is a suite of these multi-dimensional deflagration, detonation, transition, Chandrasekhar mass explosions. Right? It's almost orthogonal. The theoretical relation is almost orthogonal to what's observed. Okay? So while there were a decent number of successes for Chandrasekhar mass explosions, the observables do not actually match that well to the theory. Okay. It does better than some models, but it was not a slam dunk by any stretch. Furthermore, getting to the states where you have a white dwarf at the Chandrasekhar mass turns out to be very difficult. The main problem has to do with what happens to fuel, to the hydrogen-rich material, when you put it on the surface of a white dwarf. So it's nuclear fuel. It, if you get it hot and dense enough, it wants to fuse. And when it fuses, it releases a lot of energy, enough to eject the material off the surface of the white dwarf. So if you want to start with a white dwarf of, say, 1 solar mass and go to 1.4, you need 0.4 to stay on the white dwarf. And it's not good if that material keeps fusing and ejecting itself off of the surface. What this plot is showing is the accretion rate of the hydrogen-rich material onto the surface of the white dwarf of mass here. And the region where you can actually keep the hydrogen fit material on the surface and burn it stably into helium is actually a pretty narrow regime. So it's something like a factor of a few in accretion rate. So if you want to actually grow the white dwarf from, say, 1 solar mass up to 1.4, you have to live in this regime here. Okay. Furthermore, that hydrogen is burned to helium. That helium eventually will also want to do some nuclear fusion when it gets hot and dense enough. And if you make the equivalent plot for helium-rich material, that stable burning regime is up here somewhere. They actually don't overlap. Okay, so if you are in a regime where you can burn hydrogen and helium, you cannot burn the helium into carbon. Right? It seems to basically be impossible, at least in my opinion, impossible to start with hydrogen and grow a white dwarf from 1 solar mass up to 1.4. You just can't do it because the hydrogen will fuse to helium, and the helium will then eject itself from the surface. As a result, when you try to predict what the 1A rate is, you run into problems. This is what's known as the delay time distribution. So it's what the 1A rate is after a burst of star formation if you wait some time. So 1 gigayear, the observed rate is something like, something like a few by 10 to the minus 13 1As per solar mass per year, and it falls as something like a power law. All these colored lines are showing predictions from binary population synthesis calculations, where they have prescriptions for how the material stays on the white dwarf. So some of these optimistic ones can match the 1A rates, so especially with green and blue, can match the observations, but something generic for all of them is that at late times, say 10 gigayears, none of them can possibly get to the 1A rate. And that's a fairly simple piece of physics. At 10 gigayears, all you're left with are roughly solar mass stars and below. And if you're trying to accrete half of a solar mass from a 1 solar mass star, your accretion efficiency had better be very, very high. And even the most wildly optimistic pop-synth codes don't have accretion rate prescriptions that can accrete enough material to grow a white dwarf to the Chandrasekhar mass at 10 gigayears. Now I mentioned that I didn't think it was actually physically possible because of these arguments to ever get a white dwarf up to the Chandrasekhar mass. I think these binary pop-synth calculations are too optimistic. I actually don't think basically any of these will produce a 1A. Okay. There is a channel where you start with a helium-rich star, accrete from that, and burn that into carbon. So that is possible. So I think it is possible to get some of these to reach the Chandrasekhar mass, but helium-rich stars at the right accretion rates and the right masses, they actually only exist at very short delay times, like below 100 megayears or so. And so getting even things at 1 gigayear, much less 10 gigayears, I think is impossible in a single degenerate scenario. Something I didn't mention, furthermore, when these white dwarfs are burning the hydrogen stably into helium, they appear as what are known as super soft X-ray sources. So they're softer than regular X-ray sources and harder than UV sources, so they call them super soft X-ray sources. If you were to have enough white dwarfs burning hydrogen stably to produce the 1A rates, you predict something like 10 to 100 times more super soft sources than are observed. So there's a dearth of these kinds of stars. There's not enough of them to make 1As either. Okay, so observationally and theoretically, the rates are a big problem. It's hard to get a white dwarf up to the Chandrasekhar mass. So all that had been known for a long time. A new piece of evidence against the single degenerate scenario came out in 2010. Dan Kaitlin had a paper where he pointed out what happens when that ejecta hits the companion. Right? There should be a non-degenerate star there. People have thought about what happens to that star when it gets hit by the ejecta, but people have not discussed much what happens to the ejecta when it gets hit by the star. Okay, so here's the star, and as you can see, as you might imagine, there's some shock interaction, right? There's some energy that's dumped into the ejecta by hitting the companion. So there's a cone that's developed that has excess thermal energy. And when that thermal energy radiates, we should see it. Okay? So light curves of type 1A supernovae at early times might be able to probe that excess energy. So if black is some fiducial without any companion interaction, the green shows what happens when there's a red giant companion. It's much larger in extent, and so there's a lot more energy dumped in at later times. You can see it for longer. As compared to, say, a 2 solar mass main sequence star. It's more compact, the interaction happens earlier, and so there's less time to actually see that energy. So red giants are actually pretty easy to rule out. Turns out that red giant, there's a lower limit. At least 90% of type 1A supernovae cannot be produced by a red giant, otherwise would have seen this signature. Okay. For most type 1A supernovae, again, we don't have great observations at, say, 1 or 2 days for most type 1A supernovae. You can't rule out a low mass main sequence star companion. But in the case of the very normal 2011 FE, we had really great serendipitous observations starting at a few hours after the explosion. That early time light curve and the non-detections basically rule out the possibility of a low mass main sequence star as a companion. Should also mention that this accretion scenario where you're accreting all this hydrogen and helium from another star for millions of years, it's very hard to avoid some material not being in the circumstellar environment. However, for the vast majority of type 1a supernovae, radio and X-ray observations that have been done are all non-detections. And so there's very little material, if there's any, within the nearby circumstellar environment.
Can we rule out that the explosion does not proceed in a more beamed fashion? I mean, doesn't have to be highly beamed, but if I have a companion that is pretty far away, could it be that if, ejecta fly in one direction, that they're actually missing the companion, in which case you cannot place constraints?
Right. So, Peter, I guess, and others maybe in this room, we could talk about how the fact that 1As are extremely spherical from polarimetry. So there's very little polarized emission, polarization in the continuum. There is some in the lines, but even that's relatively low levels compared to core collapse supernovae. So 1As are very spherical, and if there were some beaming like that, I think that would be detectable. You'd also have to make up a scenario why you would avoid the companion. Okay. Right. So there are other pieces of evidence that I probably don't have time to get into about why I and many others have moved away from the single-degenerate scenario. So this is just a little table I'll start filling out about the different scenarios and the pros and cons. First, whether or not they explode. So as was discussed, there's this deflagration-to-detonation transition. We're not clear whether or not that transition actually takes place. There's a possibility that it doesn't. It's only a deflagration, in which case there's an interesting possibility that it might explain a new class of peculiar supernovae called 1ax supernovae, which I will talk about in the next slide. For other pieces of evidence, there's no sign of interaction with the companion. I've mentioned a little bit, there's the interaction when the ejecta hits the companion will suffer some effects. One of those effects will be that some of the material from the companion will get stripped off. If it's a hydrogen-rich star, you should then expect to see some hydrogen at some points in the type 1a. It's almost never been seen. It may have been seen in one case, but for the vast majority of them, hydrogen is never seen. For some of the brighter companions, we might expect to see evidence of them before the explosion if we have serendipitous imaging, like we did for 2011 FE and some other ones. There's no sign of anything at the site of the supernova. That companion should survive. Can we see that, bloated or shocked companion after the supernova has gone off, say in the center of a supernova remnant? No definitive sign of that has been seen. And as I mentioned, the rates from population synthesis calculations are off by orders of magnitude, if not infinite orders of magnitude. Okay, so I mentioned a little bit what happens if you don't allow for a deflagration-to-detonation transition. And that motivates a new class of supernova that has recently been discovered. The first prototype was 2002 CX, so that was 16 years ago. The first paper was 2005. Since then, basically I'd say 2013, early 2010s is when more and more of these 1ax supernovae were being discovered. So this is showing light curves of some of these 1ax supernovae. You can see they have a really large variety of luminosities, such that their Phillips relation, again, the peak magnitude versus how fast they're declining, their Phillips relation isn't really a relation. They're just all over the place, whereas 1As are a relatively tight correlation. Okay, so there's a large disparity. They're very heterogeneous in their light curves. Their spectra are really, really interesting. So black spectra are regular 1As. These blue spectra are some, actually it's all the prototype, 2002 CX, it's a prototype 1ax supernova. So relatively early times, it's sort of like a 1A, okay, but as you get to nebular times, these are hundreds of days. This is when you should be probing all the way to the center of the ejecta because it's optically thin. You don't see nebular emission features like you do for regular 1As. Instead, you see all this stuff. And these are very high resolution spectra. These are all lines. Okay. What you're seeing is a persistent photosphere. You're not seeing all the way through optically thin material. You're actually seeing optically thick material that produces this blanket of lines. And the explanation for that is that the supernova has left something behind. There's some wind that is persisting even after a few hundred days. Okay. So whatever exploded perhaps didn't fully explode. There might actually be something left over. One final really interesting thing I mentioned that for 1As, nothing has been seen before the explosion. For the 1AXs, there is possible signature of something, well, there's definitely a signature of something there before the explosion. So this 2012Z, there is detection right there. It's also showing some some main sequence evolutions of different stars. A helium-rich star, its main sequence looks something like that. I mentioned these super soft X-ray sources. This is again when a white dwarf is stably burning material, it should produce something like that. Okay, so the source that was seen is consistent with either the white dwarf accreting material and burning it stably, or perhaps the companion star if it's a high mass main sequence star or a helium star. Right, so this is the signature of a single degenerate scenario, something where the companion is donating material to a white dwarf, growing into the Chandrasekhar mass, and leading to explosion. Right, this is the standard 1A scenario, but this is not a standard 1A spectrum. This is not a standard 1A light curve, so something's different.
Sorry, can you go back to the previous spot? So in principle, obviously, I guess if one could choose to observe things beforehand, which obviously you can't, you'd have ways to distinguish between these different cases. It's just that this happens to be whatever
That's right.
color magnitude plot you had for this one source, and so that's why so many different things are consistent with it. But
Right. Yeah, absolutely. Yeah, you could pick all sorts of colors and
Right.
pound on it, but they went with what luck gave them. So the scenario that is being posited for 1AX supernovae is taking a helium star, a non-degenerate helium star, donating from it onto a white dwarf and growing that white dwarf up to the Chandrasekhar mass. And I mentioned before, I don't believe you can do this with a hydrogen-rich star because the hydrogen burns the helium, and then the helium will fuse unstably to carbon. However, if you start with helium, you just kind of sidestep that problem. Right, so you start with helium, you fuse the helium stably into carbon on the surface of the white dwarf, grow it up to the Chandrasekhar mass, you get core convection and then a deflagration. But if you don't allow for that detonation transition, as I said before, you only burn part of the star. Right? You need the detonation to burn the whole star and give you a regular 1A, or something like a regular 1A. If you only have the deflagration, you don't burn the whole star. So you eject some amount of material, but you leave something behind. Andrew?
They said there was just a range of allowed accretion rates where it was possible to burn stably. Are you assuming that holds and that you're in that allowed range? Or?
Yeah, so there is a certain kind of helium star as it crosses the helium Hertzsprung gap. It donates the right accretion rate. So there's a particular progenitor scenario that works.
Pardon my astrophysics, but so you've gotten rid of the whole helium envelope, but I didn't quite cotton to the fact that this is a helium atmosphere.
Get rid of the hydrogen envelope,
Is this
that's
a PAGB star, or how'd you so neatly get rid of the hydrogen?
Yeah, so this would be something where, as it was ascending the red giant branch, it's expanding, and so if it undergoes a common envelope evolution, you get rid of all the hydrogen, you're left with the helium core.
Okay, so the common envelope is a part of this
Yes.
scenario.
Yeah, I think it's part of any 1A scenario. I think they all have to undergo a common envelope evolution to get things close enough. That's right.
So there would be hydrogen out there somewhere, it's just
Somewhere, I think the timescales are such. I think the timescales are such that it would have dissipated into the ISM. I think that's right. Okay, so you have the deflagration. You don't allow for the transition, or rather, you don't put it in by hand. You only have the deflagration, and so that means you eject, say, roughly half the star as ash, but you leave half the star behind. And I went too far. That's great because now you have something that can launch this optically thick wind at late times, which matches the spectrum. And very interestingly, with the help of Gaia and some of my collaborators, have led a search for stars that match the features of the thing that's left behind. And they found a new class of stars. This is something that was published last week. A new class of stars that has all these features. They're relatively rapidly moving because when this ejected comes out, it comes out asymmetrically, and so it gives it a little kick. So these are things moving at a few hundred kilometers a second. Their surfaces are what you'd expect to see from something that was polluted by the ash of a 1AX supernova. It actually matches very interestingly to some of the simulations. So there's a new class of stars that we're somewhat confident, we're fairly confident that are the survivors of 1AX supernovae. Okay? So the scenario of Chandrasekhar mass, the single degenerate scenario of Chandrasekhar mass, deflagration, but no detonation, seems to work really well for this new peculiar class of 1AXs.
And the expectation would be for spectral polarization in this case.
So at this stage, definitely, but you know, at 100 seconds, it already looks kind of spherical. I mean, it would have some asymmetry, but it would have some asymmetry. I'm not sure. It would have more polarization than a 1A. I think that'd be right. I don't. As far as I know, there's no spectral polarimetry of 1AXs. Is there? Yeah. Okay. So the story for 1AX supernovae, this very newly discovered class, actually already has a great progenitor scenario attached to it. We do expect some of these things to explode, and there's no confusion with the deflagration-to-detonation transition. You don't have to put that in by hand. You would expect to see some sort of shock interaction when this explosion hits the companion, and indeed, for one of them, we do see evidence of shock interaction. You'd expect to see some helium as you strip it off the companion, and indeed, we do see evidence of helium. As I mentioned, there is a progenitor detection for one of them. Does the companion survive? This is something that we have not detected, but it'd be very interesting to actually find those stars. We have perhaps seen this star that's not fully disrupted. We have seen of some of these stars. There's, I think, 5 of them now. And the rates do indeed match for if you're only confined to young populations. If you only care about the 1AX rate at early times, it does match the expected rate from this scenario. So things actually look really nice for this peculiar class that people had worked on for like 5 years. It was easy in that case. For regular 1As, it is not the case. Okay? So the single-degenerate scenario has a lot of problems with it that have motivated people to move to other scenarios. I realize now that I started at 3:45, not 4, and so actually, it turns out I'm running badly on time. Okay. I'm going to try to go through this more rapidly. So there's a classical double white dwarf, a double degenerate scenario. It involves 2 white dwarfs merging, forming something that's larger than the Chandrasekhar mass. And then all the same stuff I talked about, the explosion mechanism, where you core convection, deflagration, detonation, transition, all that stuff is the same as what I've been talking about. Okay? So all you have to do is get 2 white dwarfs, add them together, and you have a supernova, right? Unfortunately, it's not that easy. So this model was proposed in '84. 1 year later, it was realized that this will not lead to a 1A, at least not easily. I'm going to say it in words because, again, I'm running out of time. So what the next few slides are going to talk about is the main problem. And the problem is that when you disrupt the companion white dwarf, it ends up in some sort of envelope around the undisrupted white dwarf. Okay? So they merge it into some object where it's a core of a white dwarf core plus disrupted material on the surface. As that material cools and starts to collect onto the surface of the core, it's impossible to avoid getting a temperature inversion where the hottest material is at the interface between the white dwarf core and the disrupted material. Where the disrupted material is diffuse, and as it compresses much more than the white dwarf does. And as a result, you can't avoid getting fusion in a shell outside of the white dwarf core. So instead of getting core burning, you get shell burning. And that shell burning evolves very differently from what you want a type 1A supernova to do. It never reaches the temperatures and densities where you can get explosive fusion. Okay, so that problem has been around for 34 years, and it is still there. We have a new physical picture, which is what this talks about, but the main outcome is still the fact that you get convective carbon shell burning instead of core carbon burning, and that convective carbon shell burning does not lead to 1A. Okay, so I apologize for skipping that, but in the interest of time, I'll just say that theoretically, double white dwarf mergers where you have a super Chandrasekhar merger remnant and expect to get a Chandrasekhar mass explosion do not work. Okay, just believe me.
Well, that's the case, provided that you have some initial mass asymmetry, right? Because for near equal mass white dwarfs, you would expect them to almost merge without tidally disrupting one another.
So the simulations that do have exactly equal mass mergers that start with asynchronously rotating, so they're not synchronous, they do disrupt both. However, if you change the mass ratio by even less than 1%, and or you allow for synchronicity, synchronous rotation, which is what we expect, if only one of them disrupts. Right, so the symmetry is broken fairly easily. All right, so there are issues with the classical double degenerate scenario. I tried to be a little more explicit about what I meant by that, but this is just a scenario where two things merge, and it's larger than the Chandrasekhar mass, and you expect to get a Chandrasekhar mass explosion. There are issues with it, believe me. Okay, I apologize for skipping that. I want to make sure I spend enough time on what I believe is the correct scenario, as opposed to relegating it to just a few minutes at the end. So there's a class of scenarios in which two detonations take place. Again, a detonation is a supersonic burning front. So first, there's a detonation in a helium layer. So this is 4 panels showing a movie. Actually, I'll just skip to the movie. Where there's a helium shell on top of a white dwarf. This is a cutaway, a 2D cutaway. Helium detonation is ignited at the pole, and you'll see it sweep around. And as it sweeps around, because it's a supersonic burning front, it sheds a shock wave into the core. And that shock wave eventually converges, and at that point it ignites a carbon detonation. So a detonation is triggered by the convergence of the shock waves from the helium detonation. So it's a double detonation scenario. It has a rich history. It was actually almost one of the first scenarios proposed. However, in the 90s, there were issues with that particular scenario. It went away. In the mid-2000s and now in the 2010s, pioneered by the group at MPA and other people, including myself, we've all been working on variants of this double detonation scenario. The one that, the progenitor scenario that involves double detonations that I want to focus on is one with 2 white dwarfs. So it's a double degenerate double detonation scenario. And in this model, 2 white dwarfs are starting to merge, so the less massive one is starting to be disrupted. Okay? That disruption actually takes place over many orbits. And at some points, as the merger is going on, the temperature and density in this accreted helium layer, this is temperature, start to get higher and higher until the helium can detonate. Let me skip ahead. No, I don't need to. Oh, what did I do? So sorry. Okay, so at some point, this helium shell will detonate. There it goes. And in this particular simulation, I don't know if it happens, but that helium detonation should then trigger a carbon detonation. Okay, so this particular variant of the double detonation scenario, we're calling the dynamically driven double degenerate double detonation scenario, or D6 for short. These actually, as I've been trying to stress, the name isn't just tongue-in-cheek. All these words are important because we have to differentiate between all these different things. It's a double detonation, but it's not a single degenerate double detonation, it's a double degenerate double detonation. And it's dynamically driven because it's happening during a merger. Okay, and that turns out to be important too, because you might imagine there's a possibility of doing this with stable accretion as well, but the ones I want to focus on involve a merger. Okay. Again, I apologize for skipping through these things so rapidly. Okay, so what happens if you take a sub-Chandrasekhar mass explosion and just detonate it, a sub-Chandrasekhar mass white dwarf and just detonate it?
So, in the standard picture of essentially unstable mass transfer, the tidal disruption takes place on the dynamical time.
Mm-hmm.
Yet you said that this thing orbits essentially for many, many orbits. I'm curious whether the simulations that you had over there accounted for gravitational wave reaction, essentially that there's also emission of gravitational waves that drive the binary a little bit inward over time. Of course, it's relatively weak, but
yeah. So for neutron stars, it certainly matters. For double white dwarfs,
well, that's what drives essentially the binary to actually reach the Rose lobe overflow.
Yeah.
And then once the Rose lobe overflow takes place, essentially you just start expanding the star, right?
Right.
Because of the mass radius relationship of white dwarfs. So that's why I said dynamical time, which should be the dynamical time of the white dwarf, but it seems to take very, very long. So I'm just curious.
Right. So yeah. So again, I didn't do those simulations. That was done by another group. But something like dozens of orbits, tens of orbits.
Is it that many orbits?
Yeah. So this is something that has been explored where people with higher and higher resolution SPH, although actually that was done with the moving mesh code. When they go to higher resolution, they're able to get lots of these relatively quiescent orbits where mass is starting to transfer, but it's not catastrophic yet. It was earlier simulations where they weren't as resolved and they weren't synchronized or they immediately merged. So it does seem to be an outcome that they get many orbits. Right. So what happens if you take a sub-Chandrasekhar mass white dwarf and just detonate it? Okay, so again, the double detonation scenario doesn't care about the mass of the white dwarf. It doesn't need a Chandrasekhar mass. So you can have almost any mass you want as long as it's dense enough to detonate. So what happens if you take, say, a 0.8 or 0.85 up to a 1.1 solar mass white dwarf and just initiate a detonation? What does it look like? So these are light curves. This is showing bolometric, UV-VRI. Different colors are, again, different masses. The gray points are a subluminous 1A, a normal 1A, this is 2011 FE in the, let's look over here, in the circles, and these diamonds are an overluminous 1A. As you can see, it actually does pretty well, I'd say. Bolometrically, it's almost spot on. The colors look decent, but there is some slight deviation. So the B band, for example, at past 15 days, it starts to drop away from the observations. And as a result, when you look at the Phillips relation, again, brighter 1As, more rapidly evolving 1As. For some of them, for say a 0.85 solar mass white dwarf, it fits inside the Phillips relation, so that's great. The single-degenerate scenario can't produce anything roughly below this, more rapidly evolving than that. There's too much mass involved. If you don't have much mass, if you have 0.85 solar masses, you can get something that rapidly evolves. So we are able to match these subluminous 1As. However, as we go to more massive things, they evolve too rapidly. Okay, and you can see that here. These drop off in B-band too rapidly. So it's not perfect, okay, but it's doing decently.
So these are calculated with what transport code?
Right, so this is a local, it's assuming LTE. So it's not assuming a non-LTE.
So that would most likely explain the...
That's great. So that's where we're going. It's in a couple slides. Okay. The spectra, like the light curves, are decent matches, but they're not perfect. So we get many of the spectral features we expect to see: strong silicon, strong calcium, this little W that shows the sulfur feature. But the features aren't perfectly lined up. So these lines are showing the velocity of the silicon and calcium features, and you can see our models are a bit too fast. Okay. So there are slight deviations, not perfect. More recently, we're about to publish some work where we did multi-D explosions. So those other ones are 1D explosions without a helium shell. Okay, the normal double detonation scenario has a helium shell, and it's obviously in multiple dimensions. So we start exploring the effects of multiple dimensions and that helium shell. The colors go from the pole where the helium shell is ignited down to the antipole. These are the equatorial ones, these red ones. The gray spectrum shows 2011 FE, a very normal type 1A supernova. And you can see we actually do decently well. The velocities have actually moved from where they were in the previous plot. So the 1D explosion had velocities that were too fast, but these multi-D equatorial regions, where most of the viewing angle is, actually do pretty well. Okay, so it seems that multi-D has helped alleviate some of the issues. However, I didn't show it, but the light curves still evolve too rapidly. I don't want to explain this, but the idea, as was alluded to, when we include non-LTE effects, so things where we're not assuming everything is in a local thermodynamic equilibrium, the hope is, and I'm actually quite confident, that some of that will alleviate some of the problems we had with the light curve. So including some non-LTE effects actually make the Phillips relation much better matched. Okay, so the models before with LTE are not in black circles, so these bare points. When we include LTE effects, and now these are calculated with CMFGen, which is a non-LTE code, it doesn't change the low mass stuff too much, but it drastically changes the light curve behavior of the more massive things. So with non-LTE, we're getting this match to the Phillips relation that I think has never been seen before in the literature. So I'm really excited about this. These bare carbon oxygen white dwarfs, which is, these are all 1D, with non-LTE does really well. Once we include multi-dimensions and include the helium shell ashes, I think we'll be well on our way to matching the observed type 1A supernovae.
Can you give a very qualitative explanation of why the non-LTE effects are more important at higher mass? Why is the effect big there?
Yeah, so for higher mass, I think the main, this is in prep, it says in prep, right? So we haven't dug deeply enough into it. The main effect is that it has to do with the fluorescence of the iron group material. So let me show a spectrum. So there are a lot of iron lines in the blue. Those iron lines absorb stuff. They don't let stuff out in the blue, and it re-radiates out in the red with primarily calcium, I believe, is the main reason. I think non-LTE reduces the amount of that fluorescence. And so they stay bluer for longer. There isn't as much re-radiation into the red. And that has to do with the level populations that are calculated in non-LTE. Why that matters more for the higher mass versus lower mass is some temperature effects, but I'm not sure off the top of my head. Sorry.
Are you worried that the 0.85 solar mass case is getting a bit to the left of the data?
Given the crudeness of this model, not at all. I'm just really excited that these things moved over.
Before you showed two different carbon-oxygen ratios with different symbols. This is just one of those two choices, right?
That's right, because CMFGen takes forever to run, like months. Yeah, so we have not pestered them.
One of them before was down where the 91 BGs are and the 99 BYs, but maybe that's not the one that's blocked.
Oh, right, that's true. Yeah. Okay. And the rates work out as well. So this is interim summary. There's lots of blue things here, right? It gets around a lot of these issues that were a problem with the single-degenerate scenario, and I think very naturally is able to explain these various observational facts. All right, the main thing I actually wanted to talk about in the last 7 minutes was what happened when we pushed on this scenario. So there are so many nice things about this D6 scenario. I wanted to try to see how far we could go with it and see if it could actually make any observable predictions, any smoking guns. And the thing we landed on, was the possibility that donor, that the companion white dwarf, might actually survive the explosion. Right, so it's starting to merge. You might expect it to be fully tidally disrupted, but if the explosion of the primary takes place before the tidal disruption of the secondary, maybe the secondary can survive, right? There's nothing that says that the merger has to be fully complete. You don't have to form a merger remnant to explode. You just have to trigger that helium shell detonation. So if that happens before this donor is disrupted, then you're going to have a surviving white dwarf, and that surviving white dwarf will be moving really, really rapidly, okay? Because the pre-supernova orbital velocities are thousands of kilometers a second. When the primary explodes, you're removing its gravitational potential, and so you just kind of slingshot the secondary away. So this is a plot showing those orbital velocities at the moment of explosion, and for white dwarfs, depending on the companion mass, the white dwarfs are all above 1,000 kilometers a second, up to 2,500 kilometers a second. So if these were indeed surviving companions of type 1a supernovae, they'd be the fastest stars in the Milky Way. Gaia Data Release 2 came very nicely, timed with this work. It came out last year in April, and so the idea was to go look for these hypervelocity white dwarfs in Gaia. Just wanted to point out how amazing Gaia has been. So it came out less than a year ago. It already has almost 1,100 citations. And most importantly for me as a theorist, it's extremely easy to use. I don't know how many of you have used Gaia data, but even for me as a naive theorist, I was able to deal with that data because it's so well curated. Okay, so many kudos to the Gaia team for making that publicly available. Okay, so April 25th came around. I was really excited about possibly observing these stars, and I was also really worried that we would get scooped because these things should stick out like a sore thumb. They're moving over 1,000 kilometers a second. All you have to do is take the proper motion from Gaia and multiply it by the parallax, divide, and you get a velocity. Okay, and so you just take two numbers, basically. So I was really worried that anyone could do this. I mean, anyone can do this. I was worried that we'd get scooped by people that were interested in hypervelocity stars who wouldn't fully understand the import of what they had discovered. If they weren't supernova people, they wouldn't know that they just confirmed this scenario that we had been working on. So I got many people, including some people in this room, to help me observe any candidate hypervelocity stars to make sure that they were actually hypervelocity, that they had large radial velocities, and that they had spectral signatures that we might expect for a surviving white dwarf. And lo and behold, we found 3 stars that I'm fairly confident are survivors of this D6 type 1a supernova scenario. So what's shown here is the posterior probability of their total galactocentric velocities for the D6 1, 2, and 3. They're all between 1,000 and 2,500 kilometers a second, exactly as we expect for a star that had been a white dwarf in a type 1 in a double white dwarf system. Okay. So the velocities are great. They also don't come from the galactic center. So the main other way to get high velocity stars is via 3-body interactions with the supermassive black hole, right? But these stars do not come from the galactic center. So the blue is showing, sorry, this is a top-down and a side view of the Milky Way. The blue is showing where it was in the past, and it does not cross Sagittarius star. They also don't come from other galaxies. So other galaxies also can generate hypervelocity stars and shoot them into the Milky Way, but these stars don't come from other galaxies. Okay, so some other mechanism had to have accelerated these stars up to 1,000 or 2,000 kilometers a second. Very weirdly, all 3 of the stars sit very close to each other in the HR diagram and far apart from any other or most other stars. So this is the white dwarf cooling track. Here's the main sequence and the giant branch. The 3, D6, 1, 2, and 3 are right here. Okay, so they're in kind of a no person's land where really very, very few stars are. And so we'd messed up and just kind of chosen artificially hypervelocity stars with bad parallaxes or something. There's no way that we would have chosen 3 stars that happen to land here, right? So they're in some weird area of the HR diagram. You might also note they're not white dwarfs, right? These are something like 10 times more puffy in radius. And the idea behind that is something we're still working on, but the idea is that during the merger, as they were starting to get tidally disrupted, a lot of energy was being dumped into them as they were being stretched. And that's why they're so much puffier now, is because they're taking a lot of that orbital energy and it's gone into lifting degeneracy. This is something we're still working on. So I mentioned that we had a lot of follow-up capability from the ground on that night and the next night. And we were able to get spectra of the 3 D6 stars within, I think, 24 hours. These are their spectra. I'm a theorist, as many of you are, I think. But I've been told, and you can sort of see by eye, these are not regular stars, right? There's no sign of hydrogen or helium. Again, if we had chosen 3 random stars in the universe, there's no way that they would be hydrogen and helium deficient. So they're very strange in that they don't have hydrogen and helium. They don't look like other stars, and they do look like each other. Okay, so that's pretty crazy, right? We chose 3 stars for their velocities, and they all end up looking very similar. They have strong signatures of oxygen and carbon and magnesium and silicon, things that you would expect for white dwarfs that had been polluted by type 1a ash. Since April 25th, we have been able to get high-res spectra. That's what's shown here. These are actually very high signal-to-noise spectra. These are all lines. Okay, so there's a tremendous number, it's a huge forest of lines that we're still in the process of modeling. Okay, so strong carbon and oxygen, a lot of what these narrow features are iron group material. Okay, so that's awesome, right? We're seeing the ash of 1A that had gone off right next to this white dwarf and got dumped onto the surface of these runaway former white dwarf companions.
What's the red?
Yeah, so that's a preliminary model where they were just trying to match some of the strongest lines. But, given how many lines there are, we're going to be working on modeling that for a while. And finally, if that wasn't enough to convince you, one of them comes from a supernova remnant. Okay, so again, the blue is where it was in the past. This is about 10 to the 5 years ago, and it pointed directly to this smudge here, which was a previously known supernova remnant. So we didn't just look at that by eye and say, oh, that's a remnant. It was actually previously known. The estimated age from that paper was 10 to the 5 years, which is exactly, puts our white dwarf or our star in the middle of that. And the estimated distance is also where this star would have been 10 to the 5 years ago. So kinematically, it seems to line up very nicely. This remnant is also the furthest one off of the plane. Okay, so it must be coming from some old population. It's not a core collapse supernova. It's very likely a 1A remnant. So that's great. So we have a 1A remnant, a likely 1A remnant that produced this hypervelocity star. I should also mention that, if you can see it down in this lower line, this is the only one of our D6 stars that has the necessary imaging to see if there is a remnant. So the other two might actually have remnants as well. We just haven't, we don't have evidence for it yet. And they'll be back up in April, and so we're gonna go after them and see if there's a remnant there. Okay. So we chose these stars out of Gaia for being hypervelocity. They looked very strange and like each other. They have the necessary compositions to be companions to 1As, and one of them, possibly all of them, come from a remnant. So we're pretty confident that what we've found is the very first detection of surviving companions to 1As, and that it does confirm this scenario. All those Ds are nice. It allows me to say that dynamically driven double-degenerate double detonations do definitely drive dwarf death. So again, there are many things that confirm why we believe this, and there's also all sorts of follow-up work that I don't expect you to read all the words about. But this happened last year. Since then, we've been working hard to try to confirm this and to explore where this can take us. So let me just mention that we're going after UV spectroscopy to try to get better handles on the exact abundances, as well as the log Gs and T effectives of these stars to see their masses and radii. That'll give us a handle on their current structures, how they got there, so why, if they started as white dwarfs, how much energy and how was it dumped in to puff them up into their current states. And then, can we run the evolution forward in time, see where they go? Where do they look like in a gigayear? Do they quickly go back to being white dwarfs, or do they remain bright for a while? Is there a reason why we didn't see more than 3? So I'm very happy we saw 3, but if they're all as bright as those 3, there should be something like a few hundred that we could have seen with Gaia, and we only saw the 3. So there's some worry that maybe this only happens for 1% of the 1As. Given all the other observational and theoretical constraints, I feel in my heart of hearts that this D6 scenario does explain the bulk of type 1a supernovae. The question is now, where are those other few hundred? Maybe they get fully tidally disrupted during the explosion, or maybe these things fade rapidly enough that Gaia was not able to see them. So I'm currently pursuing ways to look for the dimmer things using tools other than Gaia. And what I eventually want to answer is the question, do dynamically driven double-degenerate double detonations dominate dwarf death? Is the D6 scenario responsible for the bulk of type 1a supernovae? I think it is, and this is work that I and others will be doing in the next few years. And with that, I will end. Thank you very much. I apologize for going over and for rushing
We
through
have
the
maybe a
slides.
couple of minutes for 2 or 3 quick urgent questions. I'll also point out Ken is around all day tomorrow. He still has some time in his schedule. So if you would like to ask him more questions, send me an email, I'll send you his schedule, and you can sign up to meet with him.
With the double detonation, it seems like my impression is that the carbon detonation is always going to be off-center, right? And if so, how does that gel with the very low polarization and lack of asymmetric line profiles that we always see in detonations?
Yeah, so the overall explosion will still be fairly spherical, but not perfectly spherical, as you say. However, there is evidence that there is something funny with the symmetries. There have been a few studies where they look at a shift between the nebular features and the photospheric velocities, and they see that there does seem to be a different center for the two. And so that actually we do produce, again, exactly as you said, because we have this off-center detonation. So yeah, connecting that to those observations will be interesting.
Hopefully I'm going to get this right. There's some, from the observational point of view, people talk about evidence from the delay time distribution, I think for 2 channels of type 1a formation. And I was wondering if this feeds into that work, or how you feel about that inference, I guess.
So I think that notion stems from the very first days of those kinds of studies. So at the early times, roughly 2005 or so, they did find that the rate was higher in younger populations and lower in older populations. What I think they were doing, or at least what people might be thinking about, is that it's sort of like taking the delay time distribution and making it into 2 bins. So there's a young bin and an old bin, and there's a higher population, a higher rate in the young bin and conversely in the older bin. However, if you just, more recent observations, it's not 2 different populations, it's just one continuum, which is a power law, 1 over time. And that matches perfectly with the expectations for double white dwarfs. So there's no need for another population. A single population works perfectly.
All right, in the interest of time, let's thank Ken again.